Okay, so we're going to pick up where we left off in class. So this is the example I had you guys work on to wrap up in class. Again, we want to find where this function here is concave up, concave down, and where it also has points of inflection. Okay, so first thing we want to do with this is identify the domain of this function. And we know that x cannot be equal to -2 and x cannot be equal to +2. For that function, because those are the two values that make our denominator 0. Okay, so let's go ahead and differentiate this function. So using quotient rule, f prime is going to be low, d high, the derivative of the top function is 2x, minus high, d low, the derivative of the bottom function is 2x, all over low, which is x squared minus 4 quantity squared. I know I can factor that denominator, but I'm going to wait and do that at the very end. Okay, whenever I take my second derivative. So f prime here, when I distribute 2x across both terms in the numerator, we get 2x cubed minus 8x. When I distribute negative 2x across the next two terms, we get negative 2x cubed minus 2x all over x squared minus 4 quantity squared. And then I can simplify the 2x cubes cancel, so negative 8x minus 2x is negative 10x all over x squared minus 4 quantity squared. Again, I want to find the domain of f prime. The domain of f prime, again, is x can't be equal to -2, and x can't be equal to +2. Okay, so we're going to take the derivative of that to find f double prime. So that's going to be low. D high, the derivative of the top function is negative 10, minus high, d low, the derivative of the bottom function is 2 times x squared minus 4 times the derivative of the inner function 2x, just like we did in class. Okay, I had to use chain rule to take the derivative of the bottom function all over x squared minus 4 quantity squared. Sorry, x squared minus 4 raised to the 4th power, because that's the denominator squared. Okay, so just like we did in class, the two factors that they have in common are, I'm going to take the positive 10 and then also the factor of x squared minus 4. So I'm going to pull both of those out. So when I do so, that gives me f double prime of x equal to 10 times x squared minus 4. When I factor that out, that's going to leave me with negative the quantity x squared minus 4. The negative change or becomes positive, and then inside the parentheses, we're left with the factor of 4x squared. Okay. And then we're dividing that by x squared minus 4 raised to the 4th power. So I can cancel that factor of x squared minus 4 on top with one of the factors of x squared minus 4 on bottom, which is going to make f double prime of x. When I distribute the negative across both of these terms and combine like terms in the brackets, we are going to get 10 times 4x squared minus x squared is 3x squared. The opposite of negative 4 is positive 4. And then on bottom, we have x squared minus 4 cubed. I can factor that to be x minus 2 times x plus 2 raised to the 3rd power, and then I'm going to apply that exponent to each of those factors. Okay, so we have x minus 2 cubed times x plus 2 cubed. All right, and that right there is my second derivative simplified completely. Okay, so we want to identify the critical points here. So critical points are where the derivative is equal to 0. So that happens when the numerator is 0. That numerator is never going to be 0. Okay, so we want to find where the second derivative is undefined, and that happens where our denominator is 0, which occurs at x is equal to 2 and x is equal to negative 2. So we're going to make ourselves a number line or a sign chart. We're going to list the two critical points in order from smallest to largest, and then I'm going to test an interval. Now, just like the one we did in class, I don't have to test the numerator because the numerator is always going to be positive. 10 is always positive. 3x squared plus 4 is also always going to be positive. Okay, so the sign of f double prime is going to be dependent on the value of my denominator. So if I pick a value bigger than 2, let's say I pick 3, the denominator is going to be positive. Using multiplicity, the sign on the middle interval is going to be negative, and then using multiplicity, the sign on the first interval is going to be positive. So we are concave up, where the second derivative is positive, so that happens on the interval from negative infinity to negative 2, union 2 to infinity. We are concave down, where the second derivative is negative, so that happens on the interval from negative 2 to 2. And then points of inflection. So we see that the second derivative changes sign at negative 2 and 2. But when we check the first derivative is undefined at negative 2 and 2. So that's why we have to check domain to start with, because looking at the sign chart only, you would think you would have points of inflection at negative 2 and 2. But since the first derivative does not exist at those points, there are no points of inflection for that function. Okay, so make sure you check domain to start with. Okay, so this next example, really good test type question. Make sure you sketch the graph accurately. So if you need to pause the video to do that and then to get the question copied, I think that would be a good idea. I'll zoom out a little bit so you guys can do that. So it says, given the graph of y is equal to g prime of x below. So again, that's the graph of g prime, not the graph of g. Okay, so we're going to be analyzing the graph of g prime here. We are asked to answer the following. So part A asks on what interval or intervals is g increasing. Part B asks on what interval is g decreasing. For part C, says to find the value of x where g has a local max and a local min. For part D, where is g concave up and concave down? And then for part E, for what value or values of x does g have a point of inflection? Okay, so I'm going to answer all of these and also provide the justification for why the answers work. Okay, now this is going to be a big test on how well you understand the definitions that we've talked about in the last two lessons. Okay, so I'm going to do the justifications for these first, and then we'll give the answers. So part A asks on what interval or intervals is g increasing. So by definition, where is a function increasing? So g is increasing when, by definition, its derivative g prime of x is greater than 0. Okay, so we are looking for where g prime is positive. So if this is the graph of g prime is going to be positive where that graph lies above the x-axis. Okay, so this occurs on the following intervals. So the graph of g prime is positive on the half closed interval from 0 to 2, union the interval from 5 to 7. I cannot include 2 or 5 or 7. on my intervals because G prime's value at those numbers is going to be 0. It's not greater than 0. But G prime is positive at x is equal to 0 because that point lies above the x-axis. Okay, on to part B. So for part B, on what interval is G decreasing? So by definition, G is decreasing when G prime of x is less than 0. Okay, so G prime is going to be less than 0 when the graph lies below the x-axis. So this occurs on the interval from 2 to 5. Okay, I want you guys to see if you can work through parts C, D, and E on your own. So go ahead and pause the video here. Try working through those parts, and then when you're done, or if you get stuck, then you can turn it back on and we'll work through them together. Okay, so let's do part C. All right, so for part C, let's do the local max first. So G has a local max. By definition, when G prime of x changes sign from positive to negative. Okay, so when does G prime change sign from positive to negative? G prime changes sign from positive to negative at that point there at x is equal to 2. So this occurs at x is equal to 2. Again, it just asks us to find the x coordinate only. Normally when we find local maxes or local mins, we have to write them as an ordered pair unless the problem specifies otherwise. Okay, but like you guys don't know enough about calculus in order to find G's value at those points. You'll eventually be able to figure that out, just not yet. Okay, let's do the local min. Okay, so I'll do that in light blue. So G has a local min. By definition, when G prime of x changes sign from negative to positive. Okay, and this occurs at, so G prime changes sign from negative to positive at this point right here. Okay, G prime is negative to the left of that point and it's positive to the right of that point. So this occurs at x is equal to 5. Okay, let's do concave up and concave down. Okay, so let's do the definition part of that first. So G is concave up when G double prime of x is greater than 0. And this occurs at, we'll figure that out in 1 second, okay? And then G is concave down when G double prime of x is less than 0, and this occurs at, we'll figure that out in 1 second, okay? So if we want to look at the graph here, again, if that is the graph of G prime, if we want to determine G double prime is the derivative of G prime. So what are we looking for on that graph to find G double prime? We are looking for the slope. Because again, derivative tells us slope. So if we want to find G double prime, we are looking for the slope on that graph. So if G double prime is positive, we're looking for where that graph has a positive slope. So that graph has a positive slope on the interval from 0 to 1. It also has a positive slope on the interval from 3.5 to 6. And this should be on, not at. Okay, and then g double prime is going to be less than 0 where the graph has a negative slope. Okay, so the graph has a negative slope on the interval from 1 to 3.5. Union 6 to 7. Okay, so for what value or values of x does g have a point of inflection? So I'm going to do the justification for that first. So g has a point of inflection where g prime of x exists, because that's the first condition that has to be met, and the second one is where g double prime of x changes sign. All right, so the first derivative has to exist at the point, and the second derivative has to change sign. Okay, so where does the second derivative change sign? So I'm going to do in yellow where the second derivative is positive. So second derivative is positive there, and the second derivative is positive here. And then I'm going to do where the second derivative is negative in blue. Okay, so second derivative is negative here, and the second derivative is also negative there. So the first derivative exists everywhere because there's points at every single value on the interval from 0 to 7. So if we're trying to find where the second derivative changes sign, so this occurs at x is equal to 1. That's the first point. The next point is x is equal to 3.5. And the last point is at x is equal to 6. Okay, so that's how you find the points of inflection for that graph. So really good problem. It illustrates the same stuff that we've been talking about. It just we're doing it in a different context. This time we're analyzing things graphically. Namely, we are analyzing the graph of the first derivative. Okay, so two more things to wrap up here. So the directions here, and this is another good like AP style example, okay, says given the function f of x is equal to 4x cubed plus ax squared plus bx plus 12, where a and b are real numbers, we're told that f has a local minimum at x is equal to -1, and f has a point of inflection at x is equal to -2. We are asked to find the values of a and b. Okay. So if we're finding the values of a and b, this probably tells us that this is ultimately going to break down into solving a system of equations. Okay, so we're told that f has a local minimum at -1. Okay, well, I know then that I'm going to find f prime. Okay, so f prime is going to be 12x squared plus 2ax plus b. And if there is a local minimum at -1, that means that -1 has to be a critical point for our function. And because this derivative is in polynomial form, the only critical points are going to occur where that first derivative is equal to 0. So I know that f prime of -1 has to be equal to 0. Okay, so when I plug -1 in the place of x, we get 12 times -1 squared plus 2a times -1 plus b. And that's going to make 12 minus 2a plus b has to equal 0. Okay, so that allows me to say that 2a like minus b is equal to 12. Okay, so that's the first equation in my system of equations. Okay, next we have that f has a point of inflection at -2. So point of inflection pertains to the second derivative. F double prime of x is going to be 24x plus 2a. So point of inflections occur at the critical point of the second derivative. Again, because this second derivative is a polynomial, the only critical point is going to be where the second derivative is equal to 0. So I'm going to set f double prime of -2 equal to 0. So I'm going to plug -2 in the place of x. So we get 0 equal to -48 plus 2a, which means that 2a is equal to 48, and a is going to be equal to 24. And once we have the value of a, I can go ahead and plug into this equation here to figure out the value of b. So that's going to make 48 minus b equal 12, which makes b equal 48 minus 12, so b is equal to 36. So a is 24 in this problem, and b is 36. Again, good test type question, which asks the same content in a slightly different way. Okay, so last thing for us to go over in this lesson is the second derivative test. Now, this is similar to the first derivative test in that we use it to test for local extrema. Okay, so again, let me just review this really quick. First derivative test says that when you find your critical points, if your first derivative changes sign from positive to negative at some point, then you have a local maximum at your point. And if the first derivative changes sign from negative to positive at a point, you have a local minimum. Okay, now the second derivative test is done differently. And to be honest, we don't use the second derivative test very often in calculus, but there are some circumstances where it comes in handy. Okay, so I want to make sure that we know how to do this just in case the situation arises in the future where it's necessary for us to use. I don't like using it very often because it's more work taking the second derivative of a function. But again, there are some circumstances that you'll look at next year in calculus where it is advantageous to use this. Okay, so let's take a look at each part. So first part says, if f prime of c is equal to 0 and f double prime of c is less than 0. So what is that saying? That is saying if f prime of c is equal to 0, you have a horizontal tangent on a graph that is concave down. That's f double prime of c being less than 0. So if you have a horizontal tangent on a graph that is concave down, then at that point, you have a local maximum. Okay, similarly, if you look at the statement below, it says if f prime of c is equal to 0 and f double prime of c is greater than 0. So that is saying if you have a horizontal tangent on a graph that is concave up, then at that point, you have a local minimum. Okay, so we're just going to do one example here, taking a look at how we utilize the second derivative test to find local mins and local maxes. All right, so the directions here ask us to find the local extrema for the function f of x equal to -3x to the 5th power plus 5x cubed. Okay, utilizing the second derivative test. All right, so let's take a look at this one. We have the function f of x equal to -3x to the 5th. plus 5x cubed. All right, so again, anytime we test for local extrema, step one is to identify the domain, and the domain of a polynomial function is all real numbers. Okay, so we want to figure out where the first derivative is 0. Okay, so we're going to take the derivative of our function. So f prime of x is going to wind up becoming negative 15 x to the fourth power plus 15x squared. And because the derivative is a polynomial, the only critical points are going to be where that first derivative is equal to 0. Okay, so let's go ahead and factor this. So I can factor a negative 15x squared out. And when I do so, that leaves me with x squared minus 1. And then I can factor x squared minus 1 to be x plus 1 times x minus 1. Okay, so my critical points are going to be the values of x that make that first derivative 0, which are x is equal to 0, x is equal to negative 1, and x is equal to 1. Okay, so once we identify those critical points, what we want to do next is find f double prime, because we want to see if f double prime is positive or negative at those critical values. Okay, so f double prime is going to wind up becoming negative 60 x cubed plus 30x. Okay, so what we want to do now is we want to take these three values here and we want to identify or evaluate the second derivative at those numbers to determine whether our function is concave up or concave down at those points. Okay, so when we evaluate the second derivative at 0, that's going to wind up being equal to 0, which means the function is neither concave up nor concave down, okay? Which means there is no local extrema at the point 0, 0. Again, I plug 0 into the original function to get the y-coordinate at that point. Okay, I want to evaluate f double prime at negative 1 next. Okay, so when I evaluate f double prime at negative 1, that's going to become 60 minus 30, which is equal to 30, which means that f double prime is greater than 0. Okay, so that means that our function is concave up. So if we have a horizontal tangent on a graph that is concave up, that means we have a local min at negative 1, and then I have to plug negative 1 back into the original function to get the y-coordinate of our point. So negative 1 to the 5th is negative 1 times negative 3 is positive 3. Plus 5 times negative 1 is negative 5. And 3 minus 5 is going to be negative 2. And then we have to evaluate the second derivative at positive 1 as well. Okay, so when we evaluate the second derivative at positive 1, we get negative 60 plus 30, which is negative 30. So the second derivative is less than 0, which means that the graph is concave down. So if we have a horizontal tangent on a graph that's concave down, that tells us that we have a local max at the x-coordinate of the local max is 1, and then we can plug 1 into the original function to get the y-coordinate at that point. So that's negative 3 plus 5, which is going to be 2. Okay, so that's how you can use the second derivative test to find local mins and local maxes. Again, like I would not do this unless the problem told me to do this. I think it's faster and easier to use the first derivative test. But there are circumstances, especially when you get into Calc BC, when you start looking at like power series and Taylor series, where utilizing the second derivative test may be a better technique than the first derivative test. Okay, but make sure you know this because I'll probably ask this of you on your test just to make sure that you have this idea down. Okay, so that's it. Again, make sure you guys have your homework assignment completed for 5-4 before you come to class either on Wednesday or Friday. All right, hope you guys have a great rest of your day. Take care.